Welcome. I want today to talk about a graph, particular graph I call the Babylonian Graph. It's built by Pythagorean triples. It appeared twice this semester, once in the course 22b, because in the context of the Pythagorean theorem, just to illustrate how eternal mathematics is. Problems which have been pondered since thousands of years, and also it's an example of experimental mathematics where not much seems to be known. So it's a combination also of number theory and geometry. So the graph which we are going to look at has as vertices the integers, the positive integers, and the two vertices are connected if they build a Pythagorean triple. For example, 3 and 4, that's the most famous Pythagorean triple, so they are connected. And so what I have drawn here are the first, it's B60, just the first 60 numbers, and we connect to if they build a Pythagorean triple. I also marked out the prime ones, the primitive ones, the ones which cannot be divided. You know, if you take an example like 3 and 4 and you multiply it with 2, you get 6 and 8, and 6 and 8 is also somewhere that's here. That's not the primitive one. You just can multiply them. So it's quite an interesting graph. I don't know much about it, and I didn't think about it deeply. I mean, just a couple of hours now and then. It's a fun problem to think about it. First of all, yeah, they are the Pythagorean triples, these are the edges, and then the triangles, and that's something which I'm very excited about, the Euler brick. So you want a brick with integer side length such that all the diagonals, all the side diagonals are integers. So this actually corresponds to triangles in this graph. So in this smaller thing that didn't appear yet, but they start to appear. So 117, 44 are connected, 44, 20, 140 are connected, and 117, 240 are connected. Of course, now you can ask yourself some questions. What are the isolated points? What are the connected components in this graph, etc.? So you just see this is one of the low-hanging fruits, is that just 1 and 2 are the only isolated points. So 1 is not part of any Pythagorean triple, or 2, but every other number is part of a Pythagorean triple. And also the 3, 4, that's an isolated part. So this graph is not connected. So 3, 4 is not connected to anything else. This is kind of an isolated Pythagorean triple. So we can ask about then what are the properties of this? How does this graph grow, etc.? How does the number of components grow? How many? What is the dimension? How many complete subgraphs do you have from any size? So this is the f vector. How does it grow with? So all kind of things. So I have here kind of just formulated 4 questions, and they are actually, you can formulate them as conjectures if you are bold, but since I made only very small experiments, this is maybe foolish. You have to look further. So I believe there's only one connected component in this graph. So what happens is these guys get connected later on. And one of the reasons why I think this is true is because once you have more prime factors, so if you have multiples of these things, then they are more likely to connect. So I don't see a reason why there should be 2 infinite components. So first of all, yeah, there is an infinite component. The diameter is infinite, and you can just do that by looking at a concrete path which goes to infinity. So for example, if you go from 5 to 30, this connection here, if you go from 5 to 30, this can then repeat, right? 30 goes to 180, 108. So you can all the time just multiply by 6, and you go all the way to infinity when in the full graph. So yeah, this graph is infinite. And but in principle, it's possible that you have two infinite components, or more, or infinitely many, which do not recombine any time later. I don't believe that. I think there's only one infinite component, but maybe that's a foolish thing. Just law of small numbers. If you look at small examples. And also very interesting is the question about, are there K4 subgraphs, are there tetrahedral subgraphs? And that corresponds to hypercube Euler bricks. So Euler bricks in 4 dimensions, where now you have, this is much more, I don't think actually they exist, so perfect squares. I don't think that actually happens. And it actually might be simple to prove this. I actually expect this to be, you just make some inequalities and show that this. It's kind of interesting already here, the Euler brick case here. What this is an intersection of 3 cylinders. So it's kind of one of these classical problems in calculus, that you have the intersection of 3 cylinders, and then the intersection where all 3 intersect. That's kind of this has to be an integer point. It's unknown whether there is also whether there is a brick where the large diagonal is also an integer. That's the perfect Euler brick. So perfect, that's not known. That's a question of Euler. And but here in this case, it's also, there are probably too many equations. Even so, we actually have 4 unknowns, but then we have 6. So we have 10 unknowns. It's a Diophantine equation for 10 unknowns, and there are 6 equations. So maybe there is something. I don't believe actually there is, but you might tomorrow just actually find one, and then it's foolish. So but that's an interesting question. So if there are, also the question is, are there infinitely many? There are infinitely many Euler bricks. You can, there's a Saunderson parametrization, you can get explicit families, like the Pythagorean triples are also parametrized. And the primitive ones are, there's this formula, this famous formula of Euclid. Which, by the way, so the red ones are kind of just of the form 2pq and p square minus q square. So these pairs, these are actually harmonic functions in harmonic functions. So this is A, this is B. Even in the case when there is only one connected component, you could have one big component, but then there could be other smaller components which are not connected. Like there are actually, like 3, 4 is never connected to anything else. So there are smaller connected components. But then the question is, are there? I've not seen yet any of these not connected components which has a triangle. So the question is there somewhere kind of are there triangles in different connected components? These are disconnected Euler bricks. One Euler brick, another Euler brick, and there's no way you can go from one to the other using Pythagorean triples as connections. So I don't know. And the other thing, of course, you can look at the growth rate of various quantities, like the growth rate of number of connected components. The growth rate of F1 is already interesting. It's not so clear, right? How many are there? I think this is a question you can answer because there's this parametrization, and so the primitive ones we can estimate. The primitive ones, the number of edges, the red edges, the number of edges. This actually grows like 1 over n. And then, but then there are these multiples, right? So so that's somehow like, the growth rate of the primes, how they're relating the growth rate of the primes and growth rate of the integers. So I think that's kind of the right thing. It might be off, but that looks good at the moment. And then, of course, also with the F2, the number of Euler bricks. How does the number of Euler bricks grow? So you can also there you have parameterizations where you can get a subclass, but there are more. There are some which are not in this Saunderson parameterization. So that's this. These are kind of the low-hanging fruits here. I just I don't know yet much, but there are some obvious statements which you can do. For example, like that the diameter is infinite, that the vertex degree is finite for every vertex. Also, as a simple observation is that if you take a prime number, prime p, that's a leaf. In graph theory, we call a leaf a vertex which has only one neighbor. And indeed, that's what happens is if... Okay, that's it for today.